Hi, in this segment, I'm going to show you some important differences when you subtract two unsigned integers. The behavior of the program can be very subtle, can be very surprising at times. Okay, I have a little function f, right? It's an identity function. If you send in x, it'll give you back x. It's like f of x equal to x. That's all. Size underscore t is a type def defined in the standard header files somewhere in stdlib or something below there. It is usually an unsigned integer type on a 32-bit machine. So for us, it's an unsigned integer. We can treat it like that. So we send in an x, we get back the same x essentially. So we send in, for example, f of 2, we expect 2 to come back, which is the case. And we send 3, we'll get back 3. But we are doing 2 minus 3 in the end, right? What is 2 minus 3? 2 minus 3 is minus 1. Minus 1 is less than 0. We think it is, but when we run it, we will be surprised to see that this program is actually returning 0 to the user because of the size t. Okay, the size t is basically unsigned integer. When you subtract two unsigned integers, the resulting value can never be below 0. So this statement is always false. Okay, if this is always false, that means the whole expression evaluates to 0. Okay, so that's pretty surprising. We would expect that if we subtract two numbers, if one number is smaller than another number, the difference will be less than 0. Like 2 minus 3 is minus 1, less than 0, but that's not the case. Okay, let's look at the disassembly now. Look at the disassembly of f. Okay, let's look at the disassembly of f. F of x is equal to x is the function, so it's extremely simple now. It takes the value from EBB plus 8, which is the first argument, right, x, and put it into EAX, and that's all. Usually EAX is the register where we store the return value, so x is returned to the caller. But let's look at the main. That's where the fun part is. Okay, we called two functions, or function f 2 times, f of 2 and f of 3. So here is the call to function f here, and then another call here, right? And here the first call is f of 2, second call is f of 3. Okay, so where is the subtraction? We don't see the subtraction anywhere here. There is no subtraction whatsoever in terms of subtracting the return value from f of 2 and f of 3. It doesn't do anything. Instead, the last statement is interesting. Before the leave, the EAX register is set to 0. That means the compiler actually has already evaluated this code before even running it. The compiler knows that this program is going to actually return 0 to the caller, isn't it? Because it's setting 0 to EAX, which means the result of main will be already decided at compile time. Okay, because it knows from the size t definition being unsigned, if you subtract two unsigned numbers, the answer is always greater than or equal to 0. Okay, therefore this expression is always false. Therefore mu 0 is set to EAX, which means EAX is 0. Okay, all right, mu 0 EAX means EAX is 0. Okay, EAX is the register which contains the return value when you call a function. Okay, so we can actually put a breakpoint, right, and see what happens when you call f of 2, for example. Let's do that quickly. The return value of f of 2 is in EAX register, right? So let's put a breakpoint here and run the code, right, and print the value of EAX, which is 2, right, because we are calling f of x, which is nothing but identity function, right? And let's disassemble the main one more time and put a breakpoint at this location after calling f of 3. Okay, and let's print the state of EAX again. It must be 3 now. Okay, what about the EAX value which we are going to return to the caller? We are not doing the subtraction anywhere here. The subtraction is completely optimized away. There's no subtraction of the value returned by f of 2 and f of 3. Okay, so EAX is going to be 0, as we can see here. So the caller is going to get 0 as the answer because this expression is always false. It already found out at the compile time. Okay, that's quite amazing. All right, let's do a small change to the main function, so make it more demo friendly. Let me change this main function into something like this. Let me put this main function instead, which we can directly run it and see from command line. Okay. So I'm going to run this thing now from command line and show to you that the output is what, right? Where is the what coming from? It is coming from the else statement. F of 2 minus f of 3 turned out to be -1. -1 is not less than 0 when we take size underscore t into account. Therefore, this condition is false. Therefore, it comes to the else statement and prints the what, okay, which is quite unusual. The program is actually, I should have written 0, but it doesn't matter in this case. So as you can see, it returns the else statement. That's quite interesting, isn't it? Even though we are subtracting two numbers and we know the first number is smaller than the second number, but still the program reached the else part. Okay. All right. That's basically what I wanted to show to you, that you need to be careful when you are subtracting two unsigned numbers. Okay. You cannot assume the result will be less than 0, or it can be less than 0, right? But it cannot be less than 0 if your types are declared as size underscore t. Okay. So to summarize, make sure that f of x minus f of y less than 0 is useless. Okay. When your types are size underscore t. Okay. So this statement is dead code essentially. It's always false. Okay, that's what we learned. So be careful when you are subtracting two unsigned numbers. Okay, you should directly use less than instead of subtracting and comparing it with less than 0. Okay, if your goal is to compare the output of two function calls. All right, thank you very much. That's all.